Let me solve one numerical example using steepest descent method. The problem is as follows. So, I will have to minimize y is a function of two variables x 1 and x 2, and that is equals to 4 x 1 square plus 3 x 2 square minus 6 x 1 x 2 minus 4 x 1, subject to the condition that x 1 x 2 are lying between minus 10 to plus 10. So, this is an unconstrained optimization problem and there is no functional constraint here. Now, this shows the function plot, and here we will have to find out the minimum point. Iteration 1, we take the initial random solution, that is capital X 1, that is 0 0. Now, capital X 1 is a collection of the small x 1 and small x 2 values. We calculate the function value, that is f 1, and that is nothing but f of capital X 1, and if you substitute the values of x 1 x 2 in the objective function, so you will be getting 0.0. Now, I will try to find out the gradient of this particular the objective function. Now, gradient of this particular function is nothing but delta f is a collection of the partial derivative of f with respect to x 1, partial derivative of f with respect to x 2, and if we try to find out the gradient. So, del f del x 1, that will become 8 x 1 minus 6 x 2 minus 4, and the partial derivative of f with respect to x 2 is nothing but minus 6 x 1 plus 6 x 2. So, this is the gradient of this particular the objective function. Now, once I have got the gradient, now I can find out the value of this particular gradient with respect to capital X 1, and if I substitute the values of small x 1 and x 2 here. So, I will be getting minus 4 0. Now, the search direction is nothing but opposite to the gradient. So, minus delta f 1, and that is nothing but 4 0, because this is a steepest descent method. So, we will have to move in a direction opposite to the gradient. Now, x 2, that is the next solution, is nothing but the previous solution x 1 plus lambda 1 star multiplied by s 1. Lambda 1 star is nothing but the optimal step length, and s 1 is the search direction. To determine the optimal value of this step length, that is lambda 1 star, we follow a particular method. So, we try to find out f of capital X 2, and that is nothing but f of capital X 1 plus lambda 1 S 1. Now, if I just substitute the value here, so this will become like f of x 1 is nothing but is your 0, 0 and 0 plus lambda 1, and S 1 is nothing but 4 0. Now, this can be written as f of, so 0 plus 4 lambda 1, that is 4 lambda 1 comma 0 plus 0. So, this will become 0. Now, we substitute this in the objective function, the expression of the objective function. Now, expression of the objective function is as follows, like f of x 1 x 2 is nothing but 4 x 1 square plus 3 x 2 square minus 6 x 1 x 2 minus 4 x 1. Now, if I substitute the values for this x 1 and x 2, like x 1 is 4 lambda 1 and small x 2 is equal to 0. So, I will be getting one expression for this f x 2, and that is nothing but that is nothing but 64 lambda 1 square minus 16 lambda 1. Now, here now it has become a function of only one variable, that is lambda 1, and to find out the optimal value for this lambda 1. So, what we can do is we can find out the derivative and put equals to 0. So, we find out the derivative, that is d f d lambda 1, and that is nothing but 128 lambda 1 minus 16, and we put equals to 0 and solve for lambda 1. Now, this lambda 1 star, this will become 16 divided by 128, and that is nothing but 1 by 8. So, this is actually the optimal step length. Now, I am going to use this, the value of the optimal step length, to find out x 2, and x 2 is nothing but 0 plus lambda star is 1 by 8 into the search direction, that is 4 0, and if you simplify, I will be getting half 0. That means, small x 1 is equal to half and small x 2 is equal to 0. Now, f 2 is nothing but f of capital X 2, and if I substitute the values of small x 1 and small x 2, so I will be getting the function value, that is nothing but minus 1.0. Now, we try to find out the gradient of the function at capital X 2. Now, delta f 2 is nothing but delta f capital X 2, and if I calculate, we will be getting 0 minus 3, and that is not equals to 0 0. So, the termination criterion is not fulfilled. So, therefore, we say that x 2 is not the desired optimum point, and we will have to go for the next iterations. Now, this completes one iteration of this particular algorithm. Similarly, we will have to use a number of iterations, and ultimately you will be getting the optimal solution using steepest descent method. Now, I am just going to see the advantages of this steepest descent method. Now, this is a very fast algorithm. Now, as the search direction is opposite to the gradient, and by definition gradient is the direction along which the rate of change of the function will be the maximum. So, this is in fact the fastest algorithm. Now, this algorithm is very easy to implement and to understand, and it is very straightforward. However, it has got some limitation, which is as follows. Now, here in this particular algorithm, there is a chance of the solutions for getting trapped into the local minima. The reason is the gradient is a local property. So, there is every possibility that the solution is going to start at the local minima. The concept of local minima, let me explain. Now, supposing that I have got a function y is a function of only one variable. Now, if I just plot it, supposing that this is y, this is x, and I am getting a plot. Now, this is very hypothetical plot. Now, the plot is as follows. Now, here, so this basin is nothing but the local basin, and this is the global basin, and this is the minimization problem. This point is actually the locally minimum point, and this is the globally minimum point. Now, here there is a possibility that if we start from the local basin, if the initial solution is lying in the local basin, so there is a possibility, so gradually it is going to hit this locally optimal solution, and as there is no guarantee that the initial solution is going to lie in the global basin, I have got no guarantee that I will be getting the globally minimum solution always. So, this is one of the limitation of this particular the algorithm. Now, I am just going to discuss the drawbacks of traditional optimization methods. Now, before I start with the discussion on the drawbacks, let me tell you that till now we have discussed a few traditional tools for optimization. I started with the analytical approach and we concentrated on a problem having only one variable and we have seen how to solve it. So, after that we discussed one numerical method, namely the exhaustive search method, and we solved one numerical example also to explain its the principle. So, after that we concentrated on a direct search method, namely the random walk method, and we solved another numerical example, and at the end I discussed the working principle of one gradient based method, that is steepest descent algorithm, and its principle has been explained with the help of one numerical example. Now, with this I am just going to put the drawbacks of the traditional optimization methods. Now, in traditional optimization tools, we start with one initial solution selected at random, and the final solution depends on the quality of the initial solution. Now, if you select the initial solution in the local basin, so you will be getting the locally optimal solution, and if you are lucky enough to select the initial solution in the global basin, then only you will be getting the globally optimal solution. Now, the gradient based method like the steepest descent method is not suitable for the objective function whenever it is found to be discontinuous, because we cannot find out the gradient of the objective function. Now, here there is a chance of the solution of the gradient based method to get stuck at the local minima. Now, local minima is actually a minima which is not the globally optimal one, and we thought that that is the optimal, but there is a chance of further improvement of the solution which we could not hit. So, this is an inherent problem of the gradient based method. Now, these method, the traditional methods for optimization cannot be implemented in parallel computing. Now, what we do in parallel computing? We try to minimize the effective CPU time for a complex optimization problem, because for a complex optimization problem it takes more amount of time to give the solution. So, here what we do is we use a number of CPUs and the minimum number of CPU is 3, and we distribute the total computation in several computers, several CPUs, and we use one algorithm that is called MPI algorithm, that is message passing instruction. Now, with the help of this MPI algorithm, so the information from one computer is going to be passed to the next computer and vice versa, and these multiple CPUs are going to talk to each other, I should say, and they are going to send information to each other, and ultimately we will be getting less computation time, the effective less computation time to solve this particular the problem. Now, as the traditional optimization tool works based on only one initial solution, so we cannot implement the concept of parallel computing in case of the traditional optimization tool. Now, here in traditional optimization tool, we face some problem to tackle the optimization whenever there is or there are integer variables, and tackling the integer variables is bit difficult, and sometimes we face some problem, that is mixed integer problem, and there it creates further problem, and to solve that special type of problem. So, we use a special type of algorithm that is called integer programming technique. Now, here in traditional tools, so a particular traditional optimization tool may not be suitable to solve a variety of problems. So, it is not robust. Now, these are the drawbacks of the traditional optimization methods, and to overcome this, actually what we do, we take the help of some sort of non-traditional optimization tools. Now, before I go for this non-traditional optimization tool, let me summarize whatever I discussed on the traditional tools. We have discussed the working principle of a few traditional optimization tools. Now, out of all such tools, there is one tool which I have already discussed, that is the random walk method, in which the search direction is selected at random, and there is no guarantee that it is going to hit the optimal solution, and it may take a large number of iteration. So, in one side we have got the random walk method, and on other side we have got a very structured algorithm like the steepest descent algorithm, where the search direction is predefined, and that is nothing but the opposite to the gradient. And as I told that this is the fastest algorithm. So, on one side we have got the random walk method, other side we have got the steepest descent method, and each of the methods is having its own merits and demerits. Now, what we want is, we want some robust optimization tool which is in between of this the random walk method and the steepest descent algorithm, and it will be robust to solve a variety of complex real world optimization problem. And that is why the concept of non-traditional optimization tool has come into the picture. Now, I am just going to discuss little bit on non-traditional optimization tools. Now, these non-traditional optimization tools are working based on the principle our nature is going to follow. So, these are all nature inspired tools or biological inspired tools. Now, if I see the literature, we have got a large number of non-traditional tools for optimization. The list is very big. For example, say we have got the technique like genetic algorithm, which was proposed in the year 1965. Then we have got genetic programming, then simulated annealing, we have got evolutionary strategies, then we have got evolutionary programming and colony optimization, differential evolution, that is the modified version of genetic algorithm. Then we have got particle swarm optimization, we have got cultural algorithm. This is once again another modified version of genetic algorithms and others. The list is very big. We have got some other non-traditional optimization tools also. Now, here in this particular course, what I am going to discuss some of the non-traditional optimization tools, and I will be discussing their working principles with the help of some suitable numerical examples. For example, I am going to start with the working principle of genetic algorithm. Now, if you see the literature, we have got various versions of this particular genetic algorithm. It includes the binary coded genetic algorithm, the real coded genetic algorithm, gray coded genetic algorithm, then comes the micro GA, messy GA and so on. Now, here in this particular course, I am going to discuss in details the working principle of the binary coded genetic algorithm, the real coded genetic algorithm, the faster genetic algorithm like the micro GA, visualized interactive GA, and then I am going to discuss a special type of GA for solving the scheduling problem, and that is known as the scheduling GA. I will also be discussing the principle of simulated annealing. Now, here actually what we do is we try to model artificially the cooling process of molten metal and try to solve the minimization problem. And I am also going to discuss in details the working principle of particle swarm optimization. And here actually we are having a few advantages over the genetic algorithm. So, those things I am going to discuss in details with the help of some numerical examples. So, all such tools, the non-traditional optimization tools are having their own merits and demerits, and we will try to take their merits and we can try to overcome their demerits, and we can also develop some sort of the intelligent optimization tools. So, gradually I am just going to move towards that particular the direction.